It's usually not the okay, so yeah, I guess if the group is this small, I'm going to try to think a little bit how we can do it a little bit differently. Instead of, so for today, I prepared this. What I want to do is I at least change the schedule a little bit. So I don't know if you remember what was. I think I have to show it for today. But then I thought it's a little bit weird because then it's sandwiched between two OCT classes. You have Johannes on Friday, and we'll have it next Friday as well. Also because Johannes is a little bit more in depth with the OCT part. I thought I'd just jump in the middle and also do some OCT. So that means that we can organize it a little bit different. So now we have a block of 3 classes with OCT feeds, and then after that, I'm going to group the titles so a little bit formal, but I want to say that hi. Sorry, no, it's okay. These three classes are centered a little bit around the optical properties of plots, as I said. So that also means that I just thought of this during the weekend, so the slides are a little bit put together. So my apologies beforehand for that. Just before we get started, so not to make too big a fuss about this, but these are some of the things that will come back today. So just briefly. Input for second view, so you have meeting, you want to do calculations, recalculate what are the things that you need to know.
Powers, scattering power.
Yeah. In the end, if you want to calculate how much power is scattered, then you need to know that as well. Let's say you want to calculate the scattering efficiency of the photon. Just the range of power cross sections. That would also be a photon.
Oh wait,
yeah. We have the fact that the excess of the medium of the particle in the wavelength, of course, and then finally the size of the particle. So it's really remarkable that only with these things for things you can calculate. We have calculated camera properties. Then we talked a little bit about dependent scattering. That is also a topic that will come back frequently when we talk about that. It essentially means that that if you have a bunch of light scattering particles, you can calculate using these theories. You can calculate the properties of one particle. Then you cannot automatically assume that if you double the amount of particles, that you will also double the scattering properties. Non-linear scaling or a dependency on the volume fraction of these particles. It has become known as dependent scattering. Then to describe that dependent scattering, we had these two properties, two functions, the pair foundation function and structure. Do you remember what they were?
Isn't this vector like a general vector from which you can extract all the information about the accelerators, or the distribution of the instance?
No, not what you're thinking of. You're thinking about the function, but that's confusingly has the same symbol.
Ah, the other S.
Yeah, it's the other S. Yeah. So
yeah.
Let's
the Fourier transform of the pair relation function.
yeah, that's indeed, yeah, that's a good way. To number 5, very good. I'm glad you wrote it down. So what you get in, so let's say you have a bunch of scattering particles, they are illuminated with light, and they all scatter light back towards your detector. So in order to calculate the density of the detector, what you have to do normally is first calculate the scattered fields from each of these particles, the add fields, and then square that to get the phase. So that means that if you have a bunch of particles, you will get a bunch of electric fields on the detector. These electric fields have different amplitudes and different phases. Well, if the particles are the same, the amplitudes will be the same. But the phases can be different because one particle is here, the other particle is there. The distance to the detector is not the same. So the phase. So that means that these that all these little contributions to the total electric field have different phases and they can interfere. Constructively, destructively. That process. So if they are out of phase, then basically the fields cancel and you don't have zero electricity. There's not two particles, there's many particles. And how this combined effect these different phases at the detector and works out, that is the slide of structure. It's called structure factor because it has to do with how the medium is organized. You can imagine if you have a crystal, all the scattering centers are exactly their positions are fixed, so their phase relations from in relation here to the detector there, their phases will be will follow sort of pattern. So it is related. So what you will measure will then be related to the structure of the crystal. Particles are farther apart, then the phase differences will be different. They will measure something.
That also why there's the dependence on data.
Yeah, because if you look under another angle, then the distances will be different. Yeah, exactly. So for the crystal, that is so if you now have this random collection of particles, then the positions will be random, and the phases will be random as well. But not totally random, because if you think of scattering particles as like marbles or hard spheres, then there is a restriction in where they can be. So they cannot take. So they can take any random position within the medium, but they cannot overlap space because they have certain size. So there is a constraint on their positions. Position in the sample, better the distance from where the particle is to the detector determines the phase. So if there is this restriction to the positions, then there is also, just like a crystal where everything is fixed, here too there will be a dependence on the let's say structure of the sample. Now it turns out that you can simplify this a little bit if you assume that all the particles are identical, for example. If you assume that medium is homogeneous. So let's say that if you look at part of the medium here and you look at part of the medium there, that the density on average will be the same in particles. Also, so that the medium is isotropic, so it does not depend from which side you look at the medium. And then it turns out that the phase differences only depend on the distances between two particle pairs. So you can take in your medium, you can take any two particles, calculate the distance between them, and from that follows phase difference. So this pair correlation function is essentially a histogram or a distribution of distances between two particles or between particle pairs. And then you realize that these two were related because the position determines the phase and phase determines what you measure. These two were related by the matrix. But we'll encounter them a couple of times. So finally, the final question was how is it included if you want to calculate scattering properties? Well, the S, you were confused with the other S. So somehow we ran out of symbols in this sheet, and then so if you want to calculate scattering coefficient, very young sample. So essentially that means that all these restrictions and positions are not and you multiply density with the second cross-section. Dense mediums, so there is restrictions. We have the same factor here. We have to apply this correction term basically, which involves phase function. Here's the angle. And actually, with what angle you look at the system that you can
for a homogeneous anisotropic and this completely random material, does it just come down to just a factor, let's say 1/4?
Yes, yeah. So what the angle then here is, in this case, of course, is the angle between the incident light and the direction of observation. But if you would rotate the sample, then you would get exactly the same result. That's the isotope. And of course, if you would place your detector here or here or here, you could measure. You would measure the same here. To just and suddenly this will just evaluate to one number as a function of four. So that and then if you plot that graphically, then so for the you would assume that the sample is dilute, or if you would ignore all these effects, then you would simply get that scattering coefficient increases linearly with volume fractions, so the more particles you contain, higher the scattering coefficient. Then that would be not correct. You would have to take into account extrusion, and then you get this curve. So it still increases, but it's only very shallow in this case with integration and one day. So here you see the
Was the reach a maximum? Or if you're
that's a very good question. Actually, it has a maximum, but if you would plot this, so let's say the volume fraction here and US scattering coefficient here, then this would be the low density approximation. Okay, so what if the volume fraction is exactly 1?
That was kind of my thinking, like in that case. Yeah, basically the maximum level of particles.
So volume fraction 0 would essentially mean no particles at all, and then you would be here at 0. Yeah, that's for sure. But what would volume fraction 1 mean?
Like all the light will be scattered because it necessarily has to encounter particles.
Yeah, but if you really so it's a little bit shaky, but volume fraction 1 would imply that all the volume is taken up by particles.
Yeah.
And if the whole volume is filled with particles, that would mean no scattering at all anymore, because then the particle just behaves like the medium. So the ultimate limit here would be 0 again for volume fraction 1. Of course, it's physically not possible because you can pack these particles on the never reach volume fraction 1 because particles are spheres and you can stack them very efficiently, but the maximum volume fraction that you can reach is around 7%.
It seems like there's a discontinuity, but like suppose the volume fraction was 0.99, let's say.
0.99, and it would still be here. So what will happen is that
0.99 as in very close to that.
Yeah. Here. Yeah. Okay. So for spheres, I think the maximum you can actually reach is about 70%.
Yeah, there's
So let's go to there, 2.7. So how it will look like actually is something like this. So it will increase non-linearly, but then in the end, because let's say above 50%, it's kind of like particles and the distance between and the gaps between particles, they kind of switch roles. So the particles become the medium, the particle material becomes the medium, and the holes in between become the scattering. So there you get this decrease. So there is a certain point which can be about 50% or maybe 60, whatever. But after that it drops again. And yeah, if you ignore all the practical things and we just keep working with the equations, then it would actually that will not happen because above 0.7 you cannot go. But there will be a plateau, and it will actually decrease if you increase the next. Like think about it is basically the particles and gaps between the particles switch very.
Just one more short question. I'm just
Go ahead.
because like,
This is the fun part.
if they're all spherical, then for 0.7 they will be touching.
Yeah.
And the last 0.3 you can't get because of the space between surfaces, of course. But like in that case, there it would just be the same case as having cubical particles and then filling up the entire thing in a way, right?
Now, if you have cubical particles, then these you can neatly stack. So then
Yeah, right. Then you could actually get to one,
Yeah,
and
yeah,
then you know scatter.
yeah.
But like for circles, wouldn't it just be the same effect de facto for 0.7? Because again, the light cannot go through any way because all the circles are touching.
No, but there is still space between. Yeah, okay. So now,
Yeah,
now,
we mean
now,
that,
now it gets. Maybe I say too. I too often say that the particles are models. In fact, they are particles with a scattering efficiency of not of 1 but of 0.1. So a lot of might just go through.
Right.
So even if you would have these particles neatly arranged, some of the light will be scattered by 1, some of the light
Then for cubical particles need to be stacked.
yeah, then it would be just just as if no particles were there at all. That's the difference. Then there would be really no structure. Question number 1: what are the inputs of the size wavelength? And both of these reflected indexes, you need it's the difference between the ratio between the reflected index of the particle and the medium that goes into the scattering. So if these reflected indexes are the same, and there is no scattering, you need this contrast. And if everything is filled up with particle, then there is no contrast.
Right, thanks.
Yep. So OCT. They understand give you a lot of information already, and as I saw, I just found these slides a little bit mashed together. So some of it maybe on repeat, but never mind. So to remind you where OCT lives in the overview of imaging technologies, it sits here, just above the microscopy, showing that the depth of this image is in the millimeters, the resolution of it, and it's kind of unique. Without the microscope, you would not be able to look as deep into the tissue, but with better resolutions. Here, and the actual medical imaging techniques like PET, SPECT, and RAI. These can be imaged much deeper, of course. The whole body if needed, but the price is that the resolution is not so good. So it means that there's a special place for OCT if you need to have this resolution. Now the image resolution in OCT is mainly determined by technical characteristics of these systems. Repeat in a moment. But the imaging depth, so this axis is mainly limited by scattering. So if the light is any of these optical imaging modalities, the light has to go in, has to interact, and has to get back to the detector. And if there is too much scattering, too much absorption, and the light does not reach the detector anymore, then you have no image. So fundamentally, it's the light digital interaction that determines how deep it is. That's much very interested in that. So also the popular way of describing OCT is the analog of ultrasound imaging. In the sense that you make grayscale images of reflections. And of course, ultrasound is sound echo, it's optical echo. Show once again that you do not look as deep, but the resolution is much greater. This is a piece of steel. The spiraling structure that you see there, that's a strap net. So that's basically small structures that you can. You can also see that there is this difference in gray values. That means that you see different layers in the vision. Top, white, so staat gray, so dead cells. enjoy it. There's supposed to be that action in the this. Rooms, it's the thin layer. It's this rooms, not rich. What's not especially stronger, and that's why it is right. So that is how contrasting.
Sorry, what's the spiral again?
Sweat that. The other one is looking at the same pitch to doctors, and I would call it what's called histology. The idea there is, of course, that most of the diseases, at the end, the decision is made based on histology. So a lot of imaging done and a lot of measurements of all things. If they really want to be sure that the tissue is benign, they take the piece out, color it, and inspect it under the microscope to see if there's anything abnormal or not. So these are then the kind of images that you get really on the microscope. This is stained with some chemicals to get contrast. Based on this, the pathologist comparing that not so very good as the image, but you can see it gives you somehow a little bit the same kind of reflection. So that's not the color a little bit. Look like that. You see these layers, you can see these. So ultimately, the goal would be to not have to take this tissue out from the microscope, but perhaps we get while the tissue is still in place. We can do. All right. If it is the optical analog of ultrasound imaging, that's all nice and good, but there is an issue because the speed of sound is 15 meters per second. The speed of light is quite a bit larger. Which would mean about this much millimeter per second, which means that if we can only look 2 millimeters deep, light is 4 millimeters. That would mean that this echo would come only a few picoseconds after the light was sent in. That is really fast. The problem is there that essentially there are detectors that have picosecond resolutions. It is, let's summarize it as it is very, very challenging to measure these echo delay times. So therefore, you would need to have pulse laser to shine a very short pulse in, and then with picosecond resolution, you would have to wait for that. So we need a trick, and the trick is interferometry. So brief recap of interferometry. This is a sort of Michelson interferometer. Light source. So let's say that to start with, it's just a laser that emits one wavelength only, so a light beam of red light. It's beam splitter. Beam splitter is a half mirror, so half of the light is mirrored this way. You don't have just passes. And at the end of so the travel is further. This is called interferometry. We call this an arm. This is the one arm. This is a true mirror. It reflects the light back towards this beam splitter. In a beam splitter, half of the light is sent through. This part goes through. This part the other half goes back to the light source. So we'll ignore that part and just be interested in whatever happens. Now both will be oscillating electric fields. And if these distances in these two arms of the interferometer are exactly the same, then the fields essentially the same path, and they will be in phase. That means that there will be constructive interference, which means that you get constructive interference. Now, if I would move one of these two mirrors just a tiny bit, so that the path length in one arm of the interferometer is a little bit longer than in the other arm, then there starts to be a phase difference between two electric fields. You will still get interference pattern, but it will not be completely constructive. So there will still be interference. less than that. And if I pick the mirror position in such a way that, that there's exactly an opposite phase between the two fields, then they actually cancel each other out. And should not totally disturb it. So depending on the position of the mirror, I will get a certain signal of my okay, let's put that a little bit more formally. So here you see the same microsonic interferometer, monochromatic light source, so only one color. We have some light source emits radiation E0, which is split by these splitters. When I say the 50-50 beam splitter, that means that 50% of the power is split in two arms. So remember, power density was proportional to the square of the electric field. So if you want to know the splitting ratio of the electric fields, it becomes spectrum square root of so E0 is split into two electric fields that and then so you make a little mistake because I'll get it. And then the light is like this the reference mirror. So that's the reference arm of the other sample arm. This is where we will put the tissue from. So it's the sample mirror, which is the substrate arm. Then it gets combined to something. Explain what I did wrong. Just show you the next equation first. So at the detector, we would have to sum these two fields, summing the field from the sample arm and the reference arm, and to get the intensity at the detector, we have to be multiplied. Just take these. We can take these equations and simply work out this equation. It's not too incredibly difficult. Terms that have opposing that have the same phase opposing equation have a number of cancels. They will be just constants. And so these will square with the constant by 0. We have the same thing going on for these two terms. And then we have two terms that have depend on the length of the sample arm and the length of the reference. Two remaining terms, two remaining exponential terms, which are a function of the difference between the length of the sample arm and the length of the reference arm. The effect of 2 is here because light travels this twice. This to recognize is the complex notation, cosine function. In the end, the simple result is that the first method is constant offset. That's just due to the intensity is coming from the reference arm sample arm. Twice times 0. And you have modulated term, oscillating term, that's difference in the next two. This would be for monochromatic.
So in this
Yeah.
case,
No,
in this case, where would the tissue be?
so when you do the measurement, then you would take out this. You would take out one mirror and put the tissue there instead of the. So then the light is reflected by the tissue instead of to build up the argument, it's easier to start with just one mirror, perfectly reflecting the light. So that's nice.
So is the small mistake in fact that you can take into account the mirror, sorry, with the beam mirror again reduce the intensity by half?
Yeah, that's the mistake I made. So the prefactors are not defined.
I made the exact same mistake last week.
Yeah.
Now we're getting free energy and also less than I was like, why am I getting 2I0?
Yeah, so ignore please ignore the prefactors here. And the point is you get basically ignores the point you get a constant term. On top of that is this oscillating term that depends on the distance. Also known as the high. You also notice that if this is a stationary experiment, so the mirror is on a movie, then all the time dependence on the machines have dropped out. So this will just give you a static signal on your detector. If you remove the mirror, you will measure something else. Okay, now let's make it a little bit more complicated. So what would happen if I would have two wavelengths in this interferometry? So then my equations become a little bit more complicated. I now have the sample arm and the reference arm have two terms. That correspond to wavelength number 1 and wavelength number 2. That's the subscripts there. Lengths, of course, are still unasked. Calculation-wise, I would just have to do the same thing. I would have to first compute the total field of the detector and then multiply it with the complex construct to get the text. Because it will not fit on the screen if I write it out as a whole. I'll simplify it a little bit. So we have this 4 terms here. So the first term with the phi. With phase that is K1 times 2LS times 1 times 3. This one difference. Next percent part belongs to the same thing from sample arm. Here phase term for wavelength number 1, the reference arm. Wavelength number 2 the reference arm. Then of course that would have to be multiplied with some exponentials here. All these terms would have to be cross multiplied to get that. That would look, so all the terms are here, that would look like this. I'm pretty sure I made some mistake in here as well, so hey, that's not the point. So you'll see if we can group the terms. The trick is always if you get a mess like this, then you have to start grouping the terms and something sensible will come out. So here is for wavelength 1. We have a difference between sample and reference. And here also for wavelength 1, this is already very close one because this should be minus. This is S minus R, this is R minus S. So difference between sample and reference. So this will give me a cosine term, wavelength number 1, with difference between the sample and reference. There's another one for wavelength number 2. Minus reference minus sample. Also a cosine term, and then there is this complete mess of cross terms. The trick here is that in these terms, when we look at some wavelengths, and then all the others for that. If you look at cross terms for 3 wavelengths, and you get a little bit of a mess because of the case and the else. But also you end up with terms that are still these omegas are optical frequencies, so they are in the order of terahertz frequencies, very fast. The difference between the optical frequencies is still in the order of terahertz, so it's still very fast. And then if you look at what the detector actually does, so the detector sees this field, but has a certain response. And naturally, the light has to fall on it. There have to be electrons have to be made free, and they have to propagate. Detectors are not so fast. These typical detector response time lies in kilohertz to gigahertz range, which is magnitudes slower than this oscillation. So that means that the detector will basically not be sensitive to these oscillations. It will not see them, so they will not come through. They will not be measured. So in the end, the output of the detector is simply this sum of at least the cosines are the only terms that survive. So if I have one wavelength, I will just get one cosine term corresponding to that wavelength. If I have two wavelengths, I simply get two cosine terms. Of course, if I increase this argument, if I go to even more and more wavelengths in my interferometer, I will just get the summation of all these cosine terms. Okay, so again, so to detect interference signals, so that I mean that the detector current is only due to the differences in mirror positions, and still because of this filtering of the detector, so that there is still no time dependence. We have the stationary mirrors. So now, if I expand this argument further and further, so I put the polychromatic broadband light source, then I get to add all the simply have to add all the cosine terms. So with increasing bandwidth of the light sources, it's also increasing the wavelengths that don't need light source. And that's one wavelength, I have only one cosine for a number of cosines which I add. The signal that still looks cosine modulated. It falls off the distance between the mirrors. It's getting larger. So I see an interference pattern that the case of the distance between the mirrors is larger, but still it is centered, it's maximized, not the zero difference. Because at the zero difference, all the wavelengths are still in phase. So that's the only point where everything interferes constructed. All these cosines have cosine zero, so have a contribution of one. If I move a little bit further, if I move the mirror a little bit further, then it will be increasing out of phase. Then if I throw more money at it and buy very expensive laser with really a lot of wavelengths, then the interference pattern gets really, it's really narrow, centered really around the positions where there is no difference between the positions of the mirrors. Then I can turn the argument around. Then I can say, okay, if I have this mirror, and I know its exact position, and at some point I see this interference pattern, then I can calculate the position of that other mirror, because I will only see this very narrow interference pattern when the distances are the same. So if I see it, then I know one position where I also want. Of course, that comes with that, you can do that statement only within the accuracy of the width of this spectrum. So that, in other words, that will determine the resolution with which I can determine the location of certain reflection. We'll see later on. So then the steps to imaging are really straightforward. Actually, if the mirror is not perfect, and the signal will be less in amplitude. If I have 2 or 3 or 4 perfect mirrors, then it's not a good relation. But it isn't. If I have 3 or 4 or whatever perfect mirrors, then I will see these interference patterns at different positions. So then the last final step in this one process is to kind of model tissue as a stack of perfect mirrors. That this will allow me to image the reflection. So let's slightly a little bit. So let's have a short break. And then any questions? We're in small groups, so interrupt me anytime.
Yeah, I've got a topic question,
Yeah.
but I can answer very quick with this.
Okay, sure.
So basically, I asked, so last lecture, in the end, when everyone left, I asked you, almost like, so how do you actually know what depth you're able to sample? So we're talking about mirrors, but samples on the mirror, and we're talking about wavelengths, let's say 100 nanometer magnitude, right? So, like, how do you know how many of those internal reflections you have, basically? Well, at that point, I didn't even know about the sort of internal reflections. He said, like, well, actually, we're approaching it as a sort of, right, yeah, keeps on echoing, and you're probably about to explain. But still, then, you could, I guess, approach that as a repeated echo with sort of damping factor, right? Where each mirror each reflection like dampens the signal by, let's say, 0.8 something. But like, how do you actually get to the point where you say, well, actually, each angle attenuates the signal by een verlaagt, weet je wel, het signaal door een factor 0,7 in sterkte.
Ja, er zijn twee aspecten aan. Dus als je, stel je zou zeggen van, we gaan een weefsel opgebouwd uit weken uit stapelspiegels. Dit zijn ook allemaal niet perfecte spiegels. Maar wat je eigenlijk het probleem met dat beeld is een beetje dat je eigenlijk teruggenomen van jullie in het licht. Een deel hiervan wordt gereflecteerd en een deel gaat terug. Ja, ja. Dat is denk ik dat is één manier om naar te kijken. Bij het beeld van de spiegels is het.
Want u zegt, dit is juist het goede beeld van het kijken?
Nou, niet helemaal.
Kijk, hier zou je dus weer datzelfde krijgen. Weer. En dat zou je dan kunnen doorrekenen, wat het steeds zei. Maar dan is het nog de vraag, hoe kom je hier tot die factor 0,3 zetten? En dan, zelfs dan, ja, hoe weet je hoe lang dit doorgaat? Ja, het wordt natuurlijk steeds kleiner. Wat
uiteindelijk wil, uiteindelijk moet er dus een spiegel zijn. Dit is eigenlijk alles met het gedaan, maar uiteindelijk moet je bij dat kijken. Je hebt een bepaalde efficiëntie, dus de input moet bepalen, hoeveel power dat teruggestoten en dat bepaalt aan de grote signaal van deze. Als ik hier de volgende maar je niet van uitgaat is dat dit deeltje met licht wordt dit deeltje gesloten. Dus uitgaat is dat deze wordt belicht door deze. Dus als je het in deze termen zou zeggen, dan zet je een spiegel hier. Niet het deel wat hoger is.
Ja, maar zelfs dan, hoe haal je daar de iets uit? Stel je voor, hier zit nog een beeldje. De afstand is dus één golflengte. Maar de golflengte is 100, ja, orde 100 nanometers, 0,0 iets micrometers. Ja. Maar dan uit de reflectie, hoe weet je dan hoe diep je in je centrum zit?
Ja? Hey, dat is uit de zandstraat. Precies gecenteerde positie aan het beeld. Afstand. Zijn afstandsverschillen tussen links en rechts. Ja, in het beeldje.
Ja, maar zelfs daarvan zou ik zeggen, je meet niet daadwerkelijk die afstand, je meet die afstand modulo 7 een hoplengte.
Ja, dat zou zo zijn als je een hoplengte niet krijgt. En dan herhaalt dat in het les. Maar nu doordat je die hele wacht opent, dan zie je alleen maar zo'n heel narrow interferentiefotootje. Op het moment dat deze afstand aansluit.
Ja.
Dat is het niet. Dus uiteindelijk kijken zelf niet eens deze situatie. Kijken in deze deeltje nummer 1 krijgt deeltje nummer 2 is verderop.
En dan was het, why would we do that?
Wat gaat het als je hier zit?
She was like, why did we get? They were in the.
They were after the 60s.
Oh, wow.
Ja, nu is het gewoon veel laatste jaar. Je ziet er eigenlijk enorm veel conflicten zo te stekken dat het zo houdt is. Maar in ieder geval mensen gelegd van zodat je dus precies dit probleem krijgt als je het ziet achter.
And I don't know what year this was.
Meer context.
Let me show you.
Ja. Is dat te zeggen?
Ja, dus typisch.
That's very nice, right?
My friends were really nice.
Ja, en wat ik wil is het
Yeah,
soms
I'm
een
pretty
steeds
sure.
veel, is het aan die stel of weer soms.
I hope it's good. So I saw
Is het
yeah.
is dat per ongeluk of kan het zo één reden kunnen betekenen dat ze maar juist omdat die lange conflicten wordt totaal verkeerd ook waarvoor zijn juist afstanden dan niet zo
I guess the Ross like active in the 60s. Yeah.
Ja, dat is eigenlijk ja.
Voor mij
Ja.
dat is wel.
Oh, did not break.
If you meet the cat.
Wat er aan het zit.
Ja, dat wel.
Give a gap in. Did you try it?
Yes. I know that. But I'll try it. I'm gonna find out first. Because she's already like the available system. So my dad's thinking, okay, like we still rent it. Then one of my friends.
Or at least
Yeah, yeah. That's because the neighbor really wants to know, like,
Yes.
yeah, we'll see. Or my dad, I don't know. So we're going to just take. Well, I want the cat. Because at least the cat will be.
No,
Yeah. And
No. I don't think
Yes,
it's.
or if I.
Oh.
That'd be my last Are you friends?
or
So I think he's more independent.
Because when
It's
you-
not like,
Oh, like a leaf, you know.
but my friends, my friend is a dog sitter, and he's not like a month. And this dog owns a toothbrush. So it was just like, and then it's fine. And then she sees that half of the toothbrush is gone. The dog's not in there. It's me every day.
Right, so we put the minutes.
So it's very,
Like
the Japanese,
Right here, that's how it
that's what
oh, it was like this big, like teenagers. Teenagers. Oh,
Yeah.
So I think it starts with
I was thinking of this.
Like,
it does.
no, there's just no choice.
I don't know what's going on. I have no idea. Because I don't.
Because I was okay. So she doesn't.
No, totally wrong. Right, yeah.
So I don't know. I want
Not her problem.
Yeah. They do try last year. No, I must have also. I guess it's pretty basic programming stuff, but I suspect that the exam is a little tough on statistics. I took machine learning last year. So it's pretty fun. The exam has sucked. So the exam was much harder than the previous years. So I sort of walked out. So I because it sounds pretty fun, and now you can also get deep learning for medical imaging, which I'm excited about. You should probably just apply machine learning in images of like. Yeah, there was. I like if you're living in some because they take away. Right. So they actually go back. What is it actually? It turns out it's just distance. Like there's no magic really. It's just fitting functions. Like if you really like get down to it. But it's a bit very fun.
So maybe I should say.
Probably not this good. I did that last year, but stuff. We should just find it. Because it's so becomes very abstract. Like we've got a molecule, it's kind of like crystal, and it ends up being like there was one centimeter. At least those kind of my experience.
Move on.
I
So we ended up with this idea that if we have a light source with many wavelengths, then the interference pattern gets really narrow, and we can use that for localize the reflection if we know the position of the reference. So there, as you can measure, the calculation for 2 mirrors already was pretty ugly. So if you do that for a great many wavelengths, it gets even. But still, if you would be into it, that kind of calculation you can do. And there's another way that more or less hinges on some properties of the Dirk. Big stuff. So quick recap. This was the original situation where we had a detector current that was given by the final average squared electric field. By saying DC terms, and this will eventually be constant. In terms of density. All right. So let's write this a little bit more concise in terms of true lengths of some sample. Delta difference. That's the only thing. The only thing that matters. So 2 times the length is then round 3. If I write this cosine term as a complex in complex form, as a complex exponential, is simply this. So my detector current here is a function of delta after the exponential times k. Of course, the implicit thought always is that if you want to have the real physical signal, you have to take the real part of this complex factor. Because this would be this is a simple expression for the monochromatic case. For the polychromatic case, for the broadband case, we were simply allowed to add all these cosine terms. So, which means that if you have a lot of wavelengths, we have a spectrum, then this adding all these cosine terms basically means this integrating over the source. So we can take this complex representation of one wavelength and weight that with the source spectrum, so this is the strength of that source spectrum, and then add it. Of course, here you can see that this is exactly the Fourier transform. It means that we can obtain my vector current and vector signal as the Fourier transform spectrum, the light spectrum. Here. A few things. The limits here on minus infinity to infinity. Of course, the spectrum is work from minus infinity to infinity. There will only be a limited range of wavelengths in there, but where this isn't that range, so just plus minus. Yeah, let's make it practical, and I'll have to apologize because I'm reusing these slides, so all of a sudden my complex number is changed instead of so the switch here instead. So let's assume that we have a Gaussian shaped spectrum. So that is the equation on top of there. There's a center wave number A0. The Gaussian shape with a certain width k. Which I can rewrite a little bit, and not in terms of the width sigma, but in terms of the full width of the spectrum at half maximum. So this maximum 0, and the width, the spectral width, the wavelength position of half maximum, then that would be delta k. Somehow this has become the OCT, the OCT field. This has become the way of characterizing the spectrum. Okay, that's this is my spectrum. These are the cosine terms. The parameter for each wavelength. Take this Gaussian spectrum and integrate that over the spectrum. Wavelength from a Gaussian function is again a Gaussian function. It's convenient, so I can just look in the table what how the parameters translate into each other, and then the result is of the wavelength form is again a Gaussian function here, which is modulated by this Gaussian. This is the envelope of the signal that I will detect. This has a certain function of delta L, so the difference between it has a certain width, which is called the coherence length. Coherence length is the full width of maximum of this new Gaussian function. And it is so the OCT signal from the mirror, when I illuminate this interferometer with the broadband Gaussian light source, is again cosine modulated Gaussian function. Next slide. Yes. Yeah. Okay. So basically, again, in summary, the whole line of reasoning. If I would have monochromatic light source, then I would have an infinitely going interference pattern. If I would start moving one of these mirrors and change them. If I have multiple wavelengths, broadband light source, and the interference pattern gets narrow through this Fourier transform relationship. That means the width of this function gets narrow, which is called the coherence length. Monochromatic light source and infinitely long coherence length, which for the broadband light source are very small. The monochromatic light source, we have no localization of the reflectors because the reflector will go on infinitely. And for the broadband light source, so it's the expression with the Gaussian function. I have a localization with the accuracy of the coherence length, because this is the width of my. Coherence length determines. So let me give you two examples how that it really matters. These are two images, actually four images. I'm not really sure what this is taken at 800 nanometers. This is taken at 1300 nanometers center wavelength. So that would be the center of the source spectrum, and both these spectra have different widths. That's to note in the graph, but the result is that the coherence length of this light source is 4 micrometers. The coherence length of this light source is 15 micrometers. This is the same piece of tissue imaged with these two light sources, which you can appreciate that the resolution of the details is better. This is 4 micron coherence length. 15. What you also see, and we briefly discussed that in the break, is that for this system, it appears that you can move a little bit deeper into the system. So the scales are almost the same. It seems like we can image a little bit deeper. Do you have any idea why that is? So this is the third language. Sense wavelength of light source here. The other wavelengths are around that a little bit, but why do you think you can do it a little bit deeper? It has to do with yeah, the graph. So if you look at the scattering coefficient of tissue like tissue as function of wavelength, and it's a decreasing function of wavelength. It means that the scattering coefficient of tissue at 1300 nanometers will be a little bit lower than. For this image formation, what we need to have is you have to have light going in without being scattered, basically. Then having some scattering effect at a certain depth, and then making it back to the detector. So if the scattering coefficient is a little bit lower, then the probability of the light going in the deeper is higher. So in the end, for the longer wavelength, the lower scattering coefficient, you will measure a little bit. That's it. So it's very subtle. It's not that clearly visible, but okay. So now let's bring in all the Fourier transform properties. First is the Wiener theorem. It states that if you have a certain signal, then the autocorrelation function and the power spectrum of certain signal are related to a Fourier transform. But the power spectrum is simply just like we have for the light source, and the amount of light that is in there at the different frequencies. Do you know what the autocorrelation function is?
It's kind of like when you move to, you've got two graphs and you can sort of slide them over each other and then calculate the area. Yeah, it's a little.
Yeah.
Let's explain it.
Yeah, that's in general what the convolution is. But if you do that with the same function, then it's an autoconvolution or autocorrelation. You basically take a signal and you multiply it with a shifted copy of itself, and you see how big the overlap is between the signal and its shifted version. If you have a signal that's varies very slowly in time, for example, then if you would move it a little bit, it would be still very similar, and the autocorrelation would be high. If it is really fluctuating very hard, and then even small shifts would. So that's one. The other property is that a convolution or a correlation in one domain, corresponds to a multiplication in the conjugate domain, the Fourier conjugate domain, time frequency. Basically, math that if you have two functions h and t, h and g of function of time, you calculate the convolution of these. So you take the signal, you multiply it with the shifted version of the next of the other function, and then calculate the area v. Get the same results if you take the Fourier transform of both these functions and multiply it. So that is property 2. And property 3 is that if you shift a function in one domain, then that will result in a modulation. So the first one, in conjugate Fourier. So that means that if you have a function of x of t that has a Fourier transform x omega, then shifted version of x t minus some shift t0 will give us omega, the modulation, cosine to. Now let's go back to this to the signal formation. What we had. So if you look at the signal here, so the field term, basically here is the electric field reference arm, and the center arm. The only difference between these two is the length that they travel. So if you take one, so the field in one arm is simply a little bit shifted version of the field in the other. So what this interferometer actually calculates is an autocorrelation, it's a correlation between the two fields. Source field, by 2, and then it's actually multiplied by a time shifted version of itself. The detector acts as a sort of integrator because it has this response time. So what this does in hardware basically is this whole convolution operation. multiply a signal with time shifted version of itself, and then integrate. So this whole operation will have cost. Then the first theorem, the linear theorem, said that the hot correlation in one domain equals power split to the other domain. So what that tells us is actually what we already found a little bit earlier on, that the detector signal can be written as the Fourier transform of the power split. So this is then the linear theorem that then the other way around. If I have power spectrum and take the Fourier transform, I get an autocorrelation function. So here, power spectrum, that's function. Detectors. Then we can, so that would be, so that here that would be SK, so the detector signal written as the Fourier transform of the power spectrum gives us autocorrelation function. Let's go this for now. And now I can apply the shifting theorem. If I would shift, this source spectrum to a certain central wavelength, then that would lead to modulation in the other domain. So the shift in the source spectrum, the shift over K0, leads to a modulation in the spatial and the cosine radius 1. That's the other property. So if I take so with that in mind, so again, if I would take a source spectrum of a monochromatic light source, that would be just one wavelength. Then I can calculate the Fourier signal, the OCT signal, by taking the Fourier transform. So the Fourier transform of a delta function is simply a continuum cosine. So we already have one wavelength. Then we get an everlasting cosine. If I take a more realistic spectrum, this is the experimental spectrum of time, titanium sapphire laser, so the center wavelength of 5 nanometers, full width of maximum 150. If I would take Fourier transform, of this spectrum, I would end up with this Fourier spectrum, so localized Fourier spectrum. And that's the width of this. So far, I've been moving mirrors around a little bit. That is not so convenient, of course, because it takes a long time to move mirrors. So that would mean that with my images would be actually quite slow. But this is basically how it's going to be supposed to be. I just move a mirror. This red spot would then be the location from which the echo was derived, and by scanning the tissue, you build up reflectivity as a function of depth, and you move the sample or the whole system to the next location. And that is there. So instead of using a single detector, instead of using a single detector that measures basically the distances sequentially, we can use a single. We can use a spectrometer. So that is a detector that detects all wavelengths in parallel. So we still have a light source that emits broadband light. Instead of measuring all these wavelengths simultaneously and varying the position of the mirror, we split this broadband light in all its constituents, and in the spectrometer, each of these wavelength bands gets its own detector. And that has the benefit that you can stop moving around this reference mirror, and that has the benefit of things getting much faster. So why does this work? Well, simply put, we can take the same set of equations and now write them as a function of wave number. The expressions and the data will change. So each pixel of the interferometer, I it's still lies this interference function. Each pixel of the front way calculating this. Each pixel of the spectrum and each pixel will see the same kind of results, just following the steps that led to that. But now we have a single sample distribution. So it's still as functional value these pixels still has the same form. Instead of varying delta L, I now vary K. And because these two were because the spatial signal in the signal indicator domain were related to the Fourier transform, it really does not matter which one I measure. If I'm measuring the spatial domain by varying the mirror position and I take the Fourier transform, I get the spectrum. But the other way around also works. If I measure the spectrum and I take the Fourier transform, I get the spatial information. So yeah, just reiterates that one. So what you in the end get is you take the spectrum, take and make Fourier transform, you get your location. More and more mirrors is the superpositions. So again, it's just this is the one I was listening for. So the raw measurements now looks like this. So this is the output of the spectrometer. On this axis we have wave number, wavelength, which was cosine modulated form of the source spectrum. So the source spectrum looks like Gauss, but there is this cosine modulation on top of that. And if I take the Fourier transform of this, I get my interference. So if you take the Fourier transform of a real signal, so this is just a measurement, just coming out just a stack of numbers coming out of the spectrometer. If I take the Fourier transform of a real measurement, I get a complex answer. So real part and an imaginary part. If I would inspect that, then the real part would be given in measurements. It would also be the Gaussian function with the population of it. The imaginary part, which is plotted, it looks exactly the same. Shift the face a little bit. And if I take the envelope, amplitude, the signal that this amplitude is usually what we plot at first. So nice to fluctuate in this would be ideal. The Fourier transform, as we write down in the slides, of course, is the mathematical construct. If you do it in the computer, you have to use the discrete Fourier transform, which is possible, but that algorithm by itself is pretty slow. So the advantages that you get from using the spectral domain would then be lost because your computation time gets too high. So what you will use in practice is the so-called fast Fourier transform algorithm, which is fast because it requires that the data points on this axis and this wavelength axis are equally spaced. So that means that you have to sample at equal intervals. That's difficult because that will depend on how you organize your spectrometry. Spectrometer essentially is a grating where the light comes in, which splits it in the different wavelengths, and then you put a CCD camera over here that detects all the different wavelength bands. And what this requirement means that you would have to align and design this instrument in such a way that each of these pixels sees wave numbers in steps. It's in general not possible. Which is pity. And there is another effect these pixels are not infinitely small, they have a certain size. So even though you have a grating here that splits the light into different wavelength bands, each of these pixels will not see a single wavelength, it will see a tiny fraction. Because of that tiny fraction, the result of that is that the sensitivity of the measurement as you go deeper and deeper will decay, it will decrease. So you see here in this graph is repeated measurements of the mirror. The mirror is moved farther and farther away. And what we find then is that the intensity, so the peak intensity of the mirror, gets lower as we move farther away. This effect gets stronger. These pixels are larger. So the spectrometer is cheap and has large pixels. Then you cannot. Then you will have decay of your light very fast. So you can afford a very expensive spectrometer with a lot of narrow pixels. This is called a sensitivity roll-off. I'm not entirely sure if Johannes mentioned it. So that's one thing, and the other thing is that the sampling is normally equidistant, so and the spectrometer array is not equidistant. That will also lead to a degradation of resolution. So not only will the speeds get lower, they will also get broader. And then there's a third effect that is also present, and that is also due to practical considerations. The microspectrophotometer that I drew was pretended a little bit like all the light was traveling in free space. That's practical. So we use this optical fibers to guide the light. Which it turns out that you have to be really careful that the amount of fiber, the length of fiber, leading to the reference mirror, for example, is almost the same. Because if you have more glass, light travels through more glass fiber in one arm compared to the other one, you get an effect that is called dispersion. Means that the appearance signal is broadened. If you have more dispersion, it's broadened more. That leads to a loss of resolution. The peak gets more broad, so the resolution with which you can pinpoint certain reflection levels. I have a graph for that. So the ideal situation would be we have a spectrum here as a function of wave number. This is a nice modulation on it. I click Fourier transform, and this is the result of my Fourier. One more thing to notice here, this is the depth axis, and you can see that the depth axis here runs from -25 to 25 micrometers. And also you see that there are two peaks here, mirror locations with respect to depth 0. This is also an artifact of the Fourier transform. If you take a Fourier transform of a real signal, then the results the function is an even function, so you get a mirror copy of that. Even though you only have one reflector, you do a measurement like this with your spectrum, and you take the Fourier transform, you get two copies of the signal, one at positive distances and one at negative distances. The information contained in both is exactly the same. So in practice, what we do is to simply ignore this part. The calculation will give you that. Now, if we would take the same measurement now with different lengths of fiber between both arms of the instrument, so we would have this dispersion effect. The spectrum would the spectrum is more right. The created from the result of the created one is now this. Still, you get two copies of the signal, but the peaks are broadened immensely. So resolution is. Luckily, we can correct for that. You can do a calibration of the dispersion in the system, and afterwards make a correction to compensate. If you do that, so Here is the compensated version again. Find is that one of the mirror peaks, one of the peaks of positive distances. It's nicely recovered. It's a little bit difficult to see because the scales are different. But this step is nicely compensated, so the effective distribution is gone. And then the other one, it's actually made worse. This is just as a result of this procedure. So dispersion is an issue. You can, but you can rather robustly correct for it in post process.
The other one be worse, no problem.
Well, there's no problem because ideally it contains simple information and you throw it away anyway.
Yeah.
So now it's thrown away with even more vision. And then there is the effect of this sampling. So this still assumes that points this is not the case. So now we have to spectrum here. Structure of index, pixel index on spectrometer instead of a statement. If you were to transform on that, you would also get a signal that is broad. There too, you can do a correction, which brings it, which basically brings it back to the ideal form. So even though these effects are all there, with numerical post processing, it's possible to get the resolution back to what it should.
What is the recipe of the sample not smaller?
Yeah, because of the way that it is corrected. So this is basically this is a symmetrical correction where everything gets squeezed in basically like this, and this is more like like a squeezing here and stretching there. It's just in the this is double peak, so right, there is one issue. If I would have one mirror, then I would get this same side, but they're totally identical. So I cannot say this is the correct one and this is the one because there is no right or wrong. They are both essentially the same. What you measure is the distance between the two mirrors. In this case, the front. So let's say I would have a distance difference of 10 micrometers in this case in real life. Then the measurement would yield a difference, so the peak at 10 and the peak at -10. But if we would change the experiment now, I would make the difference, the true difference in the interferometer of -10 micrometers, but exactly the same result. Now this would be the peak that actually represents the location. This would be the mirror. But I cannot know beforehand which one it is. So that means that if I would now not have only one mirror, but I will take a piece of tissue where some of the reflections are positive distances from the mirror, and some of the reflections are negative distances from the reference mirror. Both will give me copies of the same signal. So if I'm careful enough to make sure that all the reflections are far away from zero, then all my copies will be neatly on this side and on that side, and I can just throw away after. If they get too close, the problem with that is the reflections get too close, the copies start to overlap. Distinguish them. Move them even further away, then I get a situation where they are neatly far enough away from zero so that they're not so they're separated. Basically, what happened here is this is then a speed image of an eye. So the subject just sits still, and the machine does nothing, and I have this reference mirror from with respect to which I'm gauging all my distances. If it is far away, relatively far away from the that's not the spatial and move it closer, because it's still move it closer. Then these two images start moving closer, so that they actually start to overlap. And as I move the mirror further away, then in the end they won't.
relatively easy to sort though. If there are exact copies, you can just always taking away to something. Because if you know that there are two copies just being mirrored, you can divide some by whatever one you could easily retrieve, right?
No, that's the point. It's not easy to retrieve because they are in the same data set. So at each there is so here it is easy because now here you know okay everything below zero is rubbish and everything above it is fine. But if the true so let's say if the true signal would I would have some tissue signal here and I would have some tissue signal here mirrored, then I can still say okay I'm going to throw this away. But now my mirror moves, so for example this way, then I get one copy that looks like this with another copy that looks like this. But it's not a copy. It's not two different data sets. It's just in one data set.
Yes, so I feel like if you were to know from which one exactly they start overlapping, I'll think about it for a bit.
Yeah.
I'm probably not winning a Nobel Prize in this break, but
you help a lot of people to
yeah.
And so the best way, the best easiest solution to make sure that it doesn't happen is to make sure that reflections are on different sides of the phone. It's a strong way. So then, for this spectral range versus time domain OCTs, the signals that you obtain are in principle Fourier equivalent because so exists this relation between the spectral domain, which we autocorrelate. That's the spectral domain and the autocorrelation domain. It does not matter where you do the measurement, you get the same information. Spectral domain is much faster because it's all moving parts. And part of that speed advantage can be traded for increased sensitivity. This expression is the Johannes gauge comes from. The spectral domain is n times more sensitive to than the time domain. That is true. They would operate at the same speed. So it's a little bit. The drawbacks are that sensitivity decreases a little bit with depth. The deeper you go, the less sensitive you are. It can be a drawback. And you have this mirror effect. Possibly overlapping instructions. But other than that, it's perfect way of doing this.
So what was the problem if you put like two previews?
Yeah.
Like I get when they overlap like zero. What is the C?
If you put them so the sensitivity increases with how deep you look. So if you put them too far apart, then this looks like an image. If the image here, then the sensitivity will be decreased. So then on the one hand, you want them as close as possible to zero to have good sensitivity, but not too close, because then they will start to overlap. That is the finger switching field that you have to find in the image. So this was the coherence length determines the resolution and depth in the image. And basically the size of the structure that you insert in the image. There is also a resolution of display, the lateral resolution. That is determined solely by so what this looks in practice is not we have a lens here. Laser beam is not too narrow, it has a certain width. This lens focuses deep on a certain position in the tissue, and light is scattered back from the tissue into the lens and then into the fiber to the way in. You do like this, you get the fiber, light comes out, it's pollinated, it's parallel by lens, and then after some time there's another lens that focuses light again. And the light going back goes the same way. Now, if you would take a very general depiction of that situation, so the light going back, flip that part and repeat this also on this side. But then you can now, let's say you can now allow for some offsets in these systems. You can allow that there's some distance between focal positions of these two beams, and also allow for some distance in this direction. The question is, if I look at this situation, how much light can I get from this fiber to this fiber? So the delta is 0, and x is 0 here, then I would have a completely symmetrical situation. I would have the fiber with the length that correlates type, that's parallel, that's the same length that focus is it. Delta is 0 and x is 0, then we propagate exactly the same length. We make it parallel, then it focus to the fiber. So then all of my lights ideally would just step back. Now the question is, what happens if there was a certain distance here between these two parts of the system? The idea is why we want to know this is because this is the part that models the light coming into the tissue, and this is the part that models the light getting back into the system. If you can calculate the overlap of the efficiency of light going from here to here under these conditions, then we can say something about how this focusing or this focusing of the light. There's a couple of parameters here that will enter into these sessions. First, we have the waist beam, that's the width of the beam. So it's the beam waist. Here is determined by the fiber size. So it will be normally the order of 9 micrometer, 10 micrometer for fibers. Then, depending a little bit on the magnification of this lens system, it will be beam width, beam waist here as well. Now let's assume that this is a 1-to-1. So these lenses are identical. We have a 1-to-1 image. So then this waist here will be the same. This Gaussian beam is not focused to a point, but is focused to a bit like this one here. So you have a width, and you also have an extent which this beam is narrow. It is called the radius. And for the detection part, we have the same thing, but now it symbols power, receiving, radius, the receiving part, waste, and the receiving. So then, if a lot of these quantities will be the same if everything is symmetrical, for argument's sake, we make a difference. So you can do that. You can do the calculations first. The first calculation is for this lens with a point reflector here. So you make a point reflector here as a function of a lateral offset x from the beam center and the function d from the exact focal point. I can calculate back how much light the efficiency represent I can get back into that. Expression looks like this, and then d here, the distance, we have an x there, that is the offset. There is the width, is d, raised part, and there is the baby length, focal length. As you can see, if you plot it, it's a pretty nice symmetrical. If you now do that, it's a little complicated all at once. If you now do it not for a point, but for a broader reflector, so like so the top graph that would be mirror. So we put it instead of a point, we put a mirror here. Some distance from the focus. So the distance from the focus to d. That means that if you mirror flip that part of the system, then the delta and the previous function. This distance. We can use the same formulas. In this case, there is no lateral offset. system just looks on a straight line, split, so X is not in there. And then there is the formula on the previous slide results reduces to this much simpler. So this is the optimum efficiency, so to say, the amount of light that you can back, the fraction of the light that you can back. If you put a mirror inside focus, then B will be 0. And the result will be 1. All like that. And if the mirror is behind the focus, so the focus will be, you get less light. That would be for a mirror. Of course, tissue is not a mirror. Tissue is this collection of particles, so to say. So they may act like all little mirrors, but not perfect mirror. So the situation then is modeled a little bit differently. So not like here, where we simply mirror the whole beam and then propagate it through to the target at the end of the system. For diffuse reflection, tissue reflection, you simply assume that that every point in the tissue acts like a new light source. It seems like a complicated situation, but the result is surprisingly simple. The result is just the same expression, but modified with a factor of 2. Really amazing. The math is terrible. If you do it, it's like 10, 20 pages of formulas, but the result is disappointing. We did an experiment, of course, to clarify this. So what you see here is an OCT signal of a scattering medium. So milk, I think it lasts milk. We knew where the position of focus was here. And we calculated the signal using these two models. So the first model would be as if all the particles in the milk acted like a mirror. Blue line, model looks like this. The signal model would be, as you can see, neatly follows the conventional explore. So that's what goes on. That's what goes on in tissue. If you have a reflector that acts like a mirror, use this formulation. Tissue like reflection. Use it. Okay. Quick. Nice. A quick quiz. Do you have any idea what you're looking at here? It's really curious if somebody saw anything.
Butterflies.
Butterfly. Yeah.
Plastic fluorescent.
So this is an ultimately zoomed in part of an OCT. This is the OCT image, which by itself is only about the size of the word ons. So that's the small scale. If I zoom in on this part here, then this would be the OCT. So what you looks a little bit like turbulence. It looks a little bit like what you have there. You have these shades, gray, that sometimes are a little bit more intense, sometimes a little bit less intense. You know how that's called? It's speckle. So let's have a short break, and then after that, I'll tell you a little bit more about speckle. Where it comes from, and how it ultimately determines the whole species. Determines the whole species. If you the whole species. If you understand speckle, you understand the whole species.
My risotto, which is the attempt to just average out what these sort of Gaussian noise and be like, what are they?
That's what most people do. But what I want to show you is that, of course, if you just want beautiful images, then that's exactly what you should do. But what I will try to argue is that if you want to know something about the optical properties of the tissue that you're imaging, then then you need to know this spectrum. Because these fluctuations will tell you something about the fluctuations that are present. But that's actually very
Last something like real sample for
yeah, of course.
a little bit of fatigue. There we are. Betreft mindset, weer precies het volgende vraag 7 toen ook de opdracht van nog gedaan. Maar ik heb niet altijd goed naar al de organisaties zo gekeken. Dus ik had dezelfde manier van organiseren bedacht. Nee, dus, ja, precies. En toen had ik zelf maar een organisatie bedacht, die ik eigenlijk mooier vind dan de organisatie die ik u voorstel. Of ja, een organisatie. Het ding is namelijk is dat ik zat dus diep na te denken over de aard, zeg maar, als over ja, de aard van die exact sampling, dat vraag ik me over na te denken. En wat we eigenlijk doen, dacht ik in de meest letterlijke zin, is we hebben een of andere. Als je in de meest algemene zin over exact sampling na te denken. Wat je dan doet, is we hebben een of andere PDF, right? Dan maken we een CDF van. Door te zeggen, we integreren van de onderkant van de termijn tot 0 tot zeg maar x. Hè. En hier hebben we PDF x, dx, ja, en dan de functie uit. CDF x. Dan zetten we die gelijk aan de uniforme verdeling. Omdat het duidelijk is te zijn. Maar je hebt een chance uit de uniforme verdeling. Kijk. Dan neem je de inverse en dan krijg je dus inderdaad x is de inverse van x. Ja. Wel nu, als we kijken naar de opdracht, dan hebben we eigenlijk als PDF hebben we het 3/8 1 plus cosinus. Zeg maar is b theta. Maar op het moment dat je die integraal doet, dan zegt u van ja, x is gelijk aan cosinus theta. Maar die CDF die verandert erdoor. Die CDF is niet de PDF van b theta, maar die wordt de facto b theta maal sinus theta. En dit was mijn hele idee over hoe ik het toen had gedaan. Is dat ik had die inverse berekend, hieruit samples genomen, toen in één keer a cosinus gezegd, zodat we dus uiteindelijk theta random kregen. Vervolgens maak je van theta random maak je een histogram, zodat je een histogram hebt van de daadwerkelijke PDF. En dan zeg je, nu deel ik al mijn centers van de bits door sinus theta. En dan krijg je dus t theta mooi terug. Het ding is met die methode, is dat je die a-cosinus pas later doet. Maar daardoor zijn je bindcenters en niet meer mooi homogeen verdeeld over het domein.
Ja.
En dat is niet zo mooi, vond ik wel eigenlijk. Ja. En het ding is, ik had dat gedaan en dit werkt dus voor de exact sampling. Ja, dus, en dan krijg je het mooi dat je overal dat krijgt. Prachtig, ja. Ook het hele spectrum en alles. En dit kan je dus doen voor die exact sampling, voor de partials. Omdat je nog steeds, ja, is het eigenlijk hetzelfde idee, telkens als je integraal doet, heb je weer dit. En voor de uniform, die, ja, ik had op zich niet al te veel gelezen, maar ik had zelf maar berekend eigenlijk vanaf, andersom berekend, wat de PDF zou moeten zijn. En toen zag ik van, ja, kwam ik eigenlijk op hetzelfde uit als wat echt Alleen voor die andere methode, dat is de enige methode waarbij je direct samples neemt eigenlijk van B-beta. De accept reject. Ja, dat is de enige methode waarbij je direct doet. En daarbij had ik normalisatie ook iets anders bedacht, namelijk dat deze helemaal niet genormaliseerd is op dit domein. Omdat de normalisatie doe je met de sinus theta. Dus je kan gewoon berekenen wat de oppervlakte hieronder is. En die oppervlakte is 9 gedeeld door 16 maal pi, zeg maar. En dat is in feite door een normalisatiefactor. Dat is dan ook eleganter.
Ja, dat
dan in het. Het ding is, ik zag toen op een gegeven moment dat hij een update versie had gemaakt van met de gate sneller. En toen zag ik bij die normalisaties, ik had er niet heel snel gekeken, zag ik bij de ene methode staan, die moet je met de sinus doen, bij de andere niet. En toen had ik iets te snel gereageerd, volgens mij is het omgedraaid. Toen later kwam ik achter, oh wacht, de aanpak was sowieso inderdaad best wel anders. En ik snap inderdaad met die accept reject dat je met sinus theta kan normaliseren.
Ja, dat was wel heel interessant, want ik stond wel.
Maar dit is ook niet te winnen.
Andere plaat, dus
dit is niet te winnen inderdaad. Ik checkte hoe laat het is. Het klopt alsnog niet inderdaad. Wat er dan wel stond, was het nog niet helemaal goed. Maar ik dacht van, eigenlijk is deze manier van normaliseren veel mooier. Omdat je die dan zijn je bins, je hebt hier superveel bins krijg je.
Nee, dat is gewoon een beetje goed.
Ja. Maar en ik dacht van, dit is eigenlijk mooi. En ook omdat het meer inzicht geeft in de aard van de...
Het probleem bij dit is dat de meeste maatschappers hebben niet zitten tegen. Omdat het die van dit constateren. Ja, dan hou je vrijheid en de boek die maakt met coördinatiesysteem. Wat makkelijk is, omdat je een functie van coaching is van het boek. Dus het is veel efficiënter om die x te zetten.
Ja, precies.
En dat heeft ook nog een benefit dat die gelijk moet onmakkelijk te investeren zijn. Dus ik denk dat die een beetje verbeterd zijn.
Ja, misschien.
Waarom ben ik zo gebrand als functie van x te schrijven? Dus het is niet
ja, precies. Ook omdat die oorspronkelijke integralen, of die integralen die je voorschrijft, die dacht ik ook die substituties van x maakt het helemaal niet echt makkelijk. Althans, ik had zelf zonder die substitutie zelf gedaan. En toen zag ik aan het eind int x substituties, maar ik dacht,
het is niet per se makkelijk.
Maar ja, oké, nee, ik las inderdaad op een gegeven moment wel dit zeggen van zijn normaal geval geïnteresseerd in niks, maar ik dacht waarom? Ja, als je in die coördinaten denkt.
Meestal weet ik dat het foto bezig is, dat heb je niet nodig. En vaak is het als je dan echt dat het stap is, dan wil je nog wel eens weten wat er schriftelijk is. Plek waarbij je maar ik vind het mooi dat het uitsluit.
Ja, nee, dan.
There's not many choices for block. There's very few choices for 6 blocks.
Ja, voor de uniform face, dat lezen. Ik neem aan dat beta iets gewoon constante eerst normaliseren. Dan kan je de CDF berekenen. En die is dan een half. Die stel je gelijk aan u. En dan kom je handmatig op dat dit je sample.
Ja, understand that.
En dan op het eind weer beter door sinus theta.
Is that also for us?
Ik moet denk twee dingen stellen door die hele sinus theta buurt. Ja, wat is dat?
I know.
Yeah. Just think one more. I do as well. Sorry,
Oh, that was the one that's been searching a room.
I think that's the normal one actually. It's 12.
I need to know.
Yep. Then the last group is. Yeah, group 3 is shorter. And group 6 is like. Yeah, but I don't think it is actually. Also, if you look. I was thinking it would be 12 plus 3. Oh, it actually makes no sense. Yeah.
Oh.
So I guess. Only the association is going to. Yeah, exactly. It's more than a master. So when I went to the analysis, register for the also choose a sort of solar biocells. Oh, anyways. Was a course which I've registered for, like it representing two choices for physiology and some biocellular cells. So it was but again then during the
I use I don't know why I'm going to take this one.
Yeah, I got it. Yeah, it's intense.
Yeah.
I mean, right, so during, let's say, there was one, 3 Cs. So this is probably. Yeah. Like, matter.
Okay, so speckle. Basically what you see here is that inside the tissue there's all these small microscopic scattering structures that all scatter back tiny little components of the electric field that needs to detect them. There's an interfield, this interfield, present as spectrum. Let's look again at the signal information. Detected signal in the spectrum domain system, so as a function of wave number, we detect a certain spectrum, and if the sample tissue will consist of only one mirror, then this is what yield result would be after flippers. The real part of the interference element is the those are modulated for parts. Plot the images and the amplitude. So in OCT use, it's B scan in OCT terminology. This is the A scan in OCT terminology. We plot the amplitude on the text. The real part here, red, is the Fourier transform. Is the real part of the Fourier transform. The spectrum of one measurement is proportional to the scattered electric field from the spectrum. We have this expression that V is proportional to the sample arm, and the reference arm intensity times the constant arm of the delta L. The reference arm field is constant. It's just a mirror. So the OCT signal itself is proportional to the field. And then of course, then we have the appearance function and the response function of the one mirror. So function gamma, it's defined as function gamma, which is the response, the max response, also associations of a single unity reflectors in a real mirror. Phase differences then, of course, the length difference between the mirror position and the length of the if I would take more than one reflector, if I would assume that they are not all perfect, then the signal okay, so this is a balloon sample. We have a few of these partial reflectors. Each of them will give this complex signal. Red and the envelope is the blue. And of course, you can have a situation that the reflectors are really close together. So we get all these kind of different contributions to the focus. This would be when the number of mirrors is really lows and distinguish a little bit the feature part of the symmetrical of these reflectors. All the signals start to overlap, and this in the end get is just one big random fluctuation due to all these random positions of the reflectors. And then in the Y is this the complex signal, where the red is the real part, and then the envelope of that is the mathematically, we can write this as the convolution of the response to the one reflector involved with a sequence of reflectors. Positions, and then we get shifted copies. We get shifted copies to the locations of these peaks of the response to the red was the result. The red part was the real part of the result of the Fourier transform. So an imaginary part, I amplitude this complex signal, and then the strand. Yeah. So now let's look into that speckle a little bit further. So we have all these little parts of the electric field that reach the detector that have independent phases from each other because the locations are different. They can have different random amplitudes because the scattering strength can be different, and we have to add all these little electric fields together to get. We can represent all these parts of these electric fields as a phasor in the real imaginary complex planes. Amplitude phase of each little part of the electric field. 1, 2, 3 in 3 reflectors. The total field is the sum of these components, which is complex step these vectors together. Mathematically, the field of the sample will be given as the sum of these individual of all these individuals. Now you could show that if the individual components all have this form, so 2 times the resulting vector, the resulting sum of that, the resulting vector will also have this form. So it will be some amplitude and some phase. The result is not now suppose that we have a random variable z in the complex planes. In this case, to represent some part of this electric field in the steam measurement. We have a joint probability density function for x and y. So just for the coordinates of this vector in the x and y. We want to know. We're interested in the distribution of the amplitude in V. So we have so these fields are random, so we have a random distribution. Tonight we have to know, I suppose. Now we want to know the distribution of the amplitude. Do you know how? Encountered ever how you have to do such a transformation? So you have probability density in one set of coordinates, and you want to transform that into another set of coordinates. Do you know how to do that? That's just a question. I've seen it enough. The trick is that you have to calculate the so-called Jacobian matrix, which is then A, V, I, A, and the permanent transformation matrix. Of that, the Jacobian matrix, and then we calculate the determinant of that matrix. It's just a number of the function itself. Then the transformation is simply so the new probability function in terms of the new coordinates is simply the old one times that determinant Jacobian. I'll give an example of that. This is really abstract. So let's say we have complex numbers. So x here is explained. We have x is a times cosinus phi, and I is a times sinus phi. If this is the relations that we have, what is then the determinant of this Jacobian matrix?
So, science and cosines,
Yeah, the
might have made a mistake. Oh, yeah, right, it is in, yeah.
so that's how I was the XDA, so it's also definitely more fragmented. So that means that if you want, if you know PDF is a major PDF. PDF joint PDF. So, for example, let the joint PDF be a normal distribution. So, P of x and y is this normal distribution, square y square, and some width sigma. We want to know the distributions of amplitude and phase. So amplitude is x squared plus y squared, and phase is expression for P of A is then simply just like I said on the previous slide. Multiply this one with A and substitute facts as so you see what happens here? Take this distribution and make the substitution here that x about this activate. Is here and multiply with this set of A. So then we have our new distribution. Joint distribution. What's tricky a little bit is that this is a joint distribution. So we have a joint distribution in this time. We convert it into a joint distribution. Even though space is not an argument. This is still the joint distribution. And actually, this is the so x and y were the x and y are the real imaginary part of the electric fields, parts of the electric field, and this is the joint probability density function of the amplitude and phase of the electric field in spectral pattern OCT, and spectral pattern that I would get by shining a laser on a rough surface, and you would also see the granular pattern. Follows the amplitudes and phases. So this is a joint probability solution. Now let's say we want a distribution of amplitude only. It means we have to calculate the marginal distribution. In this case, yeah. So you normally, if you calculate the marginal distribution for one variable, you integrate out of the other one. So this case, we would have to integrate this one over phi. It's not there, so that we can see multiplication through pi. So the distribution of amplitude is spectral pattern. This is a Rayleigh distribution. Standard distribution with of amplitude. As you can see, what the forces that carry into sigma is carried over from the underlying distribution. So the information is still that information is still.
partial probability distribution for phi would just be 1 over pi, I guess.
Yeah, indeed. I think it's then you would integrate the other variable.
It must be normalized.
But since it has to be normalized and as uniform because it was not functioning there, it becomes 1 over 2 pi. But this was then the PDF for the amplitude of the electrocution spectrum pattern. This is of course not what you would measure. If you would take a picture of the camera, you would measure the intensity. So that could be the next sentence. Intensity. That again requires another coordinate transformation now from A to 2A squared. So we would again have to calculate the Jacobian, the determined Jacobian matrix, which is simple because we know we have one variable, the E. That is 1 to A. So then if we multiply that. This with this distribution for the intensity and so on. Exponential distribution, so single. And again, interestingly, the sigma is still sigma is still the information that was present in the very much underlying normal distribution. Can simplify this a little bit. We can calculate the first moment of average intensity of this distribution. That is done by multiplying the distribution with itself and integrating the domain from 0 to infinity. You can verify this later, but if you do that, then the result of the answer is 2 sigma squared, the same 2 sigma squared is here. It's the average intensity. So by the final expression then for the probability density function for intensity in the stable pattern is this exponential distribution parameterized by mean intensity. Mean intensity carries information about the sigma that was present in the underlying distribution. This may seem like a lot of steps, but I'm going to essentially repeat a few of these steps now, but then really specific for OCT. I was a little bit lazy, so I just copied a presentation that that's on the OCT conference. The following time. So I'll just briefly also go over the introduction part because it's so much fun. So the goal ultimately is to use the optical properties, or quantify the optical properties to classify tissues. What you see here is actually a pretty hefty foreground. For example, if you it's related to over interval mutation is early cancer, pre-cancer. Tissue that person it's caused by the human papillary virus. The problem with this is that it is highly recurrent. So when patients come in, then the lesion, the suspected lesions are usually taken out, either because it's obvious or because they have to be investigated in the microscope. And because it is so recurrent, it means that it's not uncommon for patients to have 30 or so biopsies taken, treatments, treatments there. So that there's a lot of tissue that's taken out in a very sensitive area. It's really mutual. So really for these kind of applications, we think that OCT can be can really play a very vital role if we were able to do this instead of taking these biopsies. We can do an assessment, or maybe even a risk assessment if it is more likely or not to be benign. Can we leave this tissue a little longer in place, or do we have to take it out now? It really can be much. Really improves the quality of the treatment for the patients. So that is basically the background here. We did We did some pilot study together with MKI, the Cancer Hospital. We actually found that if we calculated the scattering coefficient, or we extracted the scattering coefficient, the attenuation coefficient, sorry, from OCT data, and we could see a difference in attenuation coefficient between healthy tissue and these film lesions. So that would suggest really that we would be able to diagnose in vivo based on this property. As you can also see, there is still quite a spread, so it's not a 100% accurate assessment, but still, there is good hope. Then, of course, the underlying physical idea is that if the tissue goes this transformation from normal to cancer and precancers, that there are changes in the structure of the tissue, and that these cause changes in the scattering properties, and that is the thing that we want to try to quantify. So this attenuation coefficient of the OCT signal is seen here as follows. So if you would take a homogeneous piece of tissue and we would measure the strength of the reflection as a function of depth, then we would see this decaying, just like the beers law, decaying. That's this function of depth. The rate of decay, this signal is called the attenuation coefficient. It is simply sum of the absorption and scattering coefficient. The familiar properties that we already saw. So what this process then usually involves is that you take an image, you define a region of interest in that image, and you try to fit a signal model that includes this attenuation coefficient. Expect that attenuation coefficient from that, and then the rest of the analysis. Of course, the signal, as we saw earlier on today, is not the scattering is not the only thing that causes the decay of the signal. If the reflection is out of focus, that was the story about the lenses, the confocal postcard function, you get a lower signal. So you have to take that into account in your signal. If you have a spectral domain system, then this is not optimal, then the sensitivity drops if you go in depth. So that also causes the decay. So the complete signal model is a little bit more complicated. We have decay. We have a few terms that causes decay with depth. The system with confocal postcard function, lenses, the other ones with the spectrometer, and then there is the part that is due to the scattering. So the trick is now also to cleverly calibrate the OCT system in order to factor out these terms, and then you end up only with these there, and that you can do your analysis. So let's assume that we calibrate carefully that we also accounted for. Then there's two optical properties that are left here. The symbol here, B and A, that is the backscattering coefficient, so the amount of light that scatters back within the detection system, the numerical temperature of the detection system. This whole set of subscripts that reflects the strength of the light. Here, the decay constant, the attenuation coefficient is OCT. So we accounted for the postcard function, we accounted for the roll-off. So that means that the OCT signal eventually becomes a simple expression, which we can write in simple with the group a lot of stuff in amplitude, the rest is decay. So we have a square root of 2 times an exponential 2 times z, because z is the depth, the light goes back and forth. That is the factor 2. Only this very simple exponential decay remains. So it's just like Beer's law for the OCT. The goal is to derive an expression for A, this amplitude, and see how that relates to we will do 2 assumptions here. The first is, I have not talked about that a lot yet, but this is a good moment to start doing so. The first Born approximation. The first Born approximation applied to this basically tells us that we will assume that every particle, every scattering sees the same incident field, the same incident light. So light that is scattered from one particle either goes back to the detector or goes away, but it does not illuminate another particle and then gets scattered. So it makes life a little bit simpler. So every particle just sees the same. Second thing that we'll assume is that we have this speckle pattern that we discussed a little bit earlier. It's fully without speckle means that the set of equations that I have in the slides before that they are valid. Then we will also use this tissue model that assumes that we can model tissue as identical spherical particles, hard spheres. So the restriction is again that they can touch but not have left space, and we'll also assume that they have random positions. So you can see where this is going.
How realistic is the first one?
Absolutely. It's just a model.
But it works going up apparently.
It works well.
Because the averages out or something.
That is it's of course structurally it's totally not realistic.
Yeah, I get that part. But specifically the first board.
Oh yeah, that is yeah, and there are a lot of so what it's simply when it is valid simply when the scattering is not too strong. So what we assume here is that the amount of incident light is way larger than any amount of rescattered light.
Oh yeah, no, makes sense.
And then it means that the light that every particle sees is dominated by the incident light in such a way that you can basically okay, so again, the speckle pattern what you see in the OCT images, so we're zooming in on these parts of the devices from the appearance of the different electric field contributions from the different locations. Like I said, I just called it presentation. Repeating. And the hypothesis here is that the speckle patterns carry information on the tissue organization. Using that information. What we'll see is that the information is contained in the mean amplitude, variance of the amplitude, not in the contrast. So you can, if you look at these two images, and the contrast looks more or less the same. That contains no information. You can look at the mean intensity, the variance of this intensity, variance of this intensity. How do we model? This? So in this first board approximation, we then assume that each particle experiences the same input field, which means that each particle just scatters light according to its position with a different phase. So we can find a reference particle at some position here and calculate the phases of all the other fields scattered by particles with respect to that one reference particle. The total signal can be on the detector can be given by these two stationary DC terms corresponding to the intensity from the reference arm. Sample and its interference terms. So the field and the reference arm, and then the summation of all these different field components in the sample itself. The image processing would be to filter out these static components. So what we're left with is an interference pattern, only the interference part of the signal, X given by this. Field from the reference arm that multiplies with all the electric field components contributions from all the different reflectors. So this is how it would look like if you have a lot of them. So they cannot be distinguished individually anymore. You have this huge random fluctuation. What you see here in red is the part that is then given by this expression. real, basically, what you get here is a complex representation of the OCT signal. The real part is simply that. The imaginary part is not shown. And the amplitude of that OCT signal, the complex OCT signal. So it's not possible. So the speckle was the fluctuation, the intensity fluctuation in the image. So what we refer to as speckle here is basically the fluctuation of this entity. Speckle statistics or statistics of the fluctuation of this blue. This we just discussed. So I can skip this. Oh yeah, what is? So if you, so this would be your signal, but you would process that by removing all these constant backgrounds, and you would your signal. But you can see here is that the mean of the red signal is 0, because you subtracted all the DC terms, so you're left only with the cosine, which can then be positive or negative. So the real and the imaginary part of the complex signal, the mean is 0, the variance of DC as well. Fluctuates a lot. For that envelope, the mean is not so. The variance is not so. The mean of the real part is. You can also show that starting with a couple of slides ago that the real part is normally distributed. Because it's normal distribution. The mean of x and the mean of the real part, the mean of the imaginary part of 0. The variance is the imaginary part, I would say, non-zero. That we know. And going through the steps that we did before, we also know that the envelope is radially distributed. So that was the first transformation. For the envelope we have that the mean is non-zero, so that the variance is still fluctuates. The mean and variance of the radial distribution are related to the variance of the normal distribution. So standard relations that you can look up on Wikipedia. Let's work through that. And speckle contrast. This is interesting for the radial distribution. If you calculate speckle contrast, so it's the ratio of standard deviation of the amplitude. The mean of the amplitude, that is simply a constant. 0.52. So that justifies the remark that I made earlier on that in the contrast there's no information because that the contrast is always this. Here, the mean and the variance, obviously not constants. They depend on the variance of the speckle pattern. So y, x, so the information is not in the contrast. I'm saying this specifically because this was a message that I wanted to get across on this conference, because a lot of people that were doing research and they were taking those images and they saw speckle and they thought, okay, let's use this contrast as a parameter that distinguishes between tissue types. That's basically what this derivation shows. That if you have truly developed speckle, then there is no information in the contrast. So that is not a good parameter. You know that. And they didn't. Okay, so how would that work then? Well, you would take a number of lines, a number of A scans with all these different fluctuations, and you would simply calculate the variance. So let's see if we can get an expression for the amplitude at the beginning of the signals. It said B. That would be if I would take a number of A lines at that same position, they are positions right next to each other, and I would only look at the signal that corresponds to this B. I would have a number of measurements, and from that number of measurements, I can calculate the variance. It would be the mean speckle variance corresponding to that path. So that's what you see here. X and B, I calculate the mean mean amplitude, and that is given by this relation study. Here the variance at set B. So this would be this relation I can use to get an expression for A. And in order to do that, of course, I need to use an expression for this. So step one would be to calculate an expression for x at set B. We had a relation for x already. This is sum of electric field components. The second step would be if we have x, just to calculate a variance of x from this expression. And then step 3 is to fill that in this expression. So these, if we follow these steps, then in the end we will get an expression for the amplitude. The expression for set B is then found as follows. So we define geometry with the reference particle again. So okay, that's set B. We have a few different scattering sites that are close to the round, but also contribute to the signal that we measure there. So x of set B is proportional to the real part of the sum of these components in a region around the reference. Each of these particles, remember, acts like little mirrors, so we could calculate that response to that is the convolution, this nice Fourier function with that reflector, shifted version of that reflector. So that's what you see here. This is the Hammer function here. Is simply the response to one person. Then each particle is a phasor. It's related to its position. Here measured with respect to the reference particle. So can use effect on the reference particle. Q, we encountered already again, that is the so-called scattering factor. That is Q is 2k times sine half theta. The scattering angle. F is the amplitude function of the particle, so that is the function that describes all the light as redirected. It's a spherical wave going out, so the electric field of R all the way back to the detector. We have to sum, so each of the particles gives a contribution like that. So we have to sum the last step is to integrate that over the collection angle and the mirror aperture of the. The Hammer function was this response to a perfect reflector. So if you would have a perfect reflector, you would get a response to this. If the particle is shifted to a certain position, you would get exactly the same response, but then shifted. And if the strength of the reflection is lower, then you would get this one, but then so each reflector gives a contribution in the signal that has this shape. And then, of course, because they have all different positions, these can overlap, and you don't see the individual reflection. The line is so we in the way that we model additional like identical particles, it means to say that each particle is but they do have that in phases because that depends on the position. So the index R position that is yeah, just a bit around. So this is the gate, the coherence gate, the coherence function, this need function responds to an ideal reflection. Just for completeness, this is not an equal sign, but a proportional sign because there can also be other contributions. For example, the amplitude of the incident field itself, that can also make also some conversion factors due to the detector. These are not. Okay, so we have an expression for X. Then the question is, what is the variance of it? Because that was step number 2. Well, the definition of variance is the value. It's the average square of X minus the square of the average. So just the definition of variance. The average of X was 0. So that means that the square of X is also so the variance of X is simply X squared, the average of X squared. So we can take that expression from the previous slide and calculate the average. The result is kind of impressive because we have a double sum of all the particles. So enter here on the phase differences between the different particles. Also, by squaring the amplitude function, we get to the cross section, the differential cross section over here. An integration of the numerical remains the same. So now all of a sudden, we're starting to see some familiar terms here that we encountered earlier on. So we have this difference of scattering cross sections, so scattering cross section, but then differentiate to the different scattering angles, and we have a term here that sums over phase differences between different particles, structure factor. And the expressions. What's a little bit tricky here is to determine which particles will contribute to the signal. So there is a limit to the sum that goes over only n is rho times a certain volume. So that is the number of particles. And will contribute, and that volume is given by a cylindrical volume that is a depth given by the coherence length, width, and the width is given by the waist of that beam. So basically just a definition. So what we will do for simplicity is say that if particles in that cylindrical volume, then we set the coherence relation to 1, and if it's outside that volume, we will set it to 0, so that you can at least take that one out of the equations. But we have this equation, then the last step, of course, was to multiply that with the factor of p over 2 and take the square root. So essentially, we are already pretty close to the answer. A couple of things that we can do here. We see the average of the phase differences between the different scatters. That was the structure factor, which we had before, or the transform of the pair correlation function. So we can substitute this part for the double sum gives us factor n, and the phase differences here gives us factor s2, or also because p is related to theta, we can also parameterize this one as theta. So that simplifies the structure factor. Set the clear transform of the pair correlation function. So simplifying even further, we get this result. We get the number of particles here in front, proportional to the number of particles. We get the differential scattering cross section, which tells us how much light is scattered into different angles. The structure factor for the sample organization, the whole thing is integrated over the detection. So if we look at this is again for people at this conference, point again. If you look at the loop regime where there are no structure factors, then this would be an expression for that scattering coefficient. So the difference, if we compare these two expressions, is that we have the integration limit that is limited here to the numerical aperture, which is 0 angles, and of course the inclusion of structure factor. So what we will get here is something that is very similar. So it's the variance here is very similar to a scattering coefficient, to an optical property. So we can analogy to this textbook expression for the scattering coefficient, we will define here the UB and A, the backscatter coefficient within the numerical aperture of the detector as well as some differential scattering cross section multiplied with structure integrated collection. So then step 3 is basically just filling in these equations and crossing out some constants, so we get a variance that is proportional to this new B and A volume, this volume resolution for the OCT system, and the median variance of the speckle pattern. So the ones containing the information is these expressions. So the amplitude, the amplitude of the variance of the speckle pattern depends on this optical property. This is the this scattering coefficient within the NA of the OCT system is the optical property that OCT is sensitive for. So if there is changes in tissue due to disease progression, this is reflected in this new NA, and that is what we will issue in OCT. Again, the speckle contrast contains no information because again, if you take the variance, you can calculate the standard deviation, if you define standard deviation on the mean, and you see that all the information terms will be used to calculate those out. So the contrast has no information. Yeah, the speckle, the mean, the variance depends on the optical properties. Property that contains the structure factors that contains information on the organization. Of course, it's so nice and good to do theory like this with experiments. And this is what Mitra did. He prepared samples using scatterers in different volume fractions. So you can calculate how many scatterers there are going to be in the volume, and then take an OCT system that we have in the lab. System there, and then just do the measurements and compare it with the theory. So here, those key images, extract the amplitude speckle pattern at a certain depth, and calculate the histogram of that. And as you can see, these histograms nicely follow the predicted value distribution and the scan of the variance. It's also very clear from the discussion on the slide. Variance neatly follows what is predicted by the preparation of the if you look a little bit, if you now take a whole OCT scan, so this is a scan in depth, where you can take various you can take the spectral amplitude of various depths and samples of A, B, or C. That indeed shows that all these locations, the spectrum is still very distributed, although at this depth, this is very low, it becomes very noisy. So maybe this is stretching it. At every depth, we see this nice gradient. So that suggests that the theory is more or less correct. So then the final result is, so we started out with an expression for the OCT signal that was kind of complicated and contained all forms of decay that you could have, instrumental and due to the sample. If you assume that these two can be calibrated, and the efficiency factors can also be calibrated, then that means that you can do absolute measurement of OCT amplitudes. We can with the theory above, we can relate this directly to the properties. So it gives us access to a quantifiable property that will or will not change as a function of the disease. That is then the next issue. This is conclusion. No, I'm just this is good enough. I had a few more slides on my feed, but Johannes is going to bore you to death with those on Friday as well. So I think this suffices for now. That's it. Yeah.
If we did the graphing part as a group, do we still have everyone individual?
If you just be sure to put your names and your student numbers on there, then I'll figure it out. Then once the questions.
Including, well, just all the questions once they're done.
Yesterday I was at someone's thesis defense. She's biomedical technology, I think, or biomedical engineer. And she used very similar to what you showed. She looked into robot cancers, and she used a spectral camera to basically measure absorption coefficients. And then use machine learning to, because the huge data sets and everything, use machine learning to actually derive some spectrum for absorption. And yeah, the results were quite impressive. There was a very clear distinction between normal cell basically and cancer cells.
Yeah.
So
that's really exciting time because so machine learning has gone so fast in the last couple of years. There's actually so what we usually were a little bit stuck in a situation where you could do the measurements and just by eye you can see differences, you can see different sectors. It's not entirely clear how you could use it to separate different groups or to the regression. Now with machine learning getting more advanced, it's all of a sudden much easier to incorporate more data and bigger data. It's really going fast now.
she didn't even use like super advanced stuff. She just used vector machines.
Yeah. Okay, so
basically
on the simple side.
Yeah, right. Basically, classification, not like neural networks. It's still quite Today is the other assignment project.
I have finished thinking, but it's a little bit on what Johannes is going to is or not going to tell you. So as soon as he's done, I know what it will exactly look like.